first of all, I'd like to thank the organizers for giving me an opportunity to speak here. I'm going to talk about the theta JT gravity and double-scale SIK model. My talk is not really directly related to the integrability or corpuscle parameters, but I hope some of you might find this interesting. So this is the plan of my talk. After a brief introduction and motivation, I will explain double-scale SIK model. Many of you are not so familiar with this, so I will explain first. And then I move on to the matrix model for this DSSIK, which is called the ETH matrix model. And I'll argue that after taking a double scaling limit of this matrix model, the theta JT gravity appears from this model. Okay. So the holography in the theta space is not so well understood. So it is highly desirable to have a very simple and tractable example of the star quantum gravity. And it turns out that two-dimensional JT gravity with a positive cosmological constant is a very useful toy model to study this problem. We have already heard about three-dimensional digital gravity in the previous talk.
Sorry,
okay.
Could you push your mic a bit higher?
Higher. Okay.
Yeah, that looks better. I think that's good.
Is that good?
Yeah.
Okay. So we have already heard about the three-dimensional version of the star quantum gravity in the previous talk by Muehlmann. But in my case, I would consider the two-dimensional version of the theta JT gravity, which might be simpler than the three-dimensional case, I guess. So in the case of the ADS version of the JT gravity, the holography is quite well understood. And the ADS version of the theta gravity, JT gravity is dual to SIK model at low energy. And this duality, holography, comes from the fact that these two models are described by the same mode called the Schwarzian mode. So they share the same degrees of freedom. So they're naturally dual to each other in a holographic sense. But if you go to the higher genus, or including the higher topology, this duality can be promoted to a duality between the JT gravity and some double scaling limit of random matrix model shown by Sarchenko Stanford in 2019. So it turns out that this JT gravity matrix model of Sarchenko Stanford can be embedded into a finite dimensional matrix model called the ATH matrix model. And this is the genus 0 eigenvalue density of this ATH matrix model. It has a finite support and two edges. And if you focus on the lower edge, low energy side of the spectrum, we recover the ADS version of the JT gravity of Sarchenko Stanford. And my proposal is if you focus on the upper edge, or the high energy side of the spectrum, it corresponds to the theta JT gravity. This identification was already suggested by these people based on bulk semi-classical picture of sine dilaton gravity. But what I did is take a double scaling limit of this matrix model directly around this upper edge and recover this zeta version of JT gravity. Okay. So basically, this slide is the one slide summary of my talk. So this is the takeaway message of my talk. So if you take a scaling limiter on the upper edge, you get the digital space. Okay. So let me briefly explain double scalar SYK model. Maybe the audience here are not so familiar with this model, so I'll talk about this model in a couple of slides. So the SYK model is a very interesting toy model for holography, proposed by, as a model of holography is proposed by Kitaev in 2015, 10 years ago. And this model is a system of n major fermions with this Hamiltonian, given by this Hamiltonian, where J is the p-body interaction coupling, which is a random coupling with Gaussian distribution. Okay. So the Gaussian nature of this random coupling is just an assumption, but which this Gaussian assumption simplifies the computation a lot. So this serves as a very tractable toy model for holography. So this Gaussian is just an assumption, which makes life easier. Okay. So Barkhus company showed that this SYK model can be exactly solvable by taking a certain limit. This is called the double scalar SYK model. And this limit is a large n limit, where n is the number of flavors of major fermions. And at the same time, we take a large p limit, where p is the number of p-body interaction in the Hamiltonian, in such a way that p goes like a square root of n. Well, in other words, we take n and p both large with p squared over n fixed. And this combination is called lambda. And this limit is called the double scalar SYK. Okay. So another thing about this limit is that if you compute the moment of the Hamiltonian, trace h to some power, and take the average of the random coupling, this moment, computation of the moment, reduces to some counting problem, combinatorial problem of the intersection number of chord diagrams. So we count the intersection of chord diagrams with a weighting factor Q is given by the minus e to the minus lambda. Lambda is p squared over n. Okay. So here is the example of the chord diagram. In this example, I'm considering trace h to the 8th power, 8 Hamiltonian insertions. So we take a trace, so we draw a circle, and we put 8 Hamiltonians around the circle, and take the average of the random coupling can be computed by the weak contraction, because we assumed this random coupling is Gaussian. So the average of the random coupling can be computed by the weak contraction. And for each weak contraction, we draw a line called chord in this business. And this is here the example of some chord diagrams coming from the weak contraction of the random coupling. And then we count the intersection numbers of this diagram. In this case, we have 2 intersections, of course, here. So this diagram comes with a factor of Q squared. And because we are taking the average of the Gaussian random variable, we have to sum over all possible weak contractions. And as a diagram, we draw all possible chord diagrams and count the intersection numbers and sum over all. Okay. And this is just a combinatorial problem. So, and if you look at the math literature, this problem has been studied by mathematicians a long time ago, and it has been solved. But for physicists, it's easier to introduce some transfer matrix. And it turns out this combinatoric circle diagrams can be solved by introducing the transfer matrix given by this. And here A plus and A minus are Q oscillator, which creates or annihilates the chords. Here N is the number of chords, it represents the number of chords. And if you act A plus, N increase by 1. And if you act A minus, N decrease by 1 with some Q-dependent factor here. And the E naught, sorry. So here E naught is depends on some normalization of the random coupling, which comes from the variance or the width of the Gaussian distribution of the random coupling. So this is some overall normalization which is related to the distribution of the random coupling. And this transfer matrix can be diagonalized in some basis parameterized by the variable theta, which is some angular variable. And the eigenvalue is given by, let's get the cosine of theta. Okay. And this eigenbasis and the overlap of this eigenbasis and the original chord number state is given by the Q-Hermite polynomial, like this. And so this problem has something to do with the Q deformation of polynomials and so on. And using this kind of machinery, you can compute the disk amplitude of DSSIK like this. So for the partition function, is given by this expression. It exponentiates the transfer matrix sandwich between the vacuum of the Q oscillator. And this has a nice integral representation in terms of the parameter theta, angular parameter theta. And this exponent is just the eigenvalue of this transfer matrix in cosine of theta. And here, the mu of theta is some measure factor given by this infinite product expression, the Q Pochhammer symbol. And this measure naturally arises because this orthogonalized, the Q-Hermite becomes orthogonal with respect to this measure. So this is a very, very brief review of DSSIK. Okay. Then I'll move on to the matrix model of DSSIK. We can construct some Hermitian matrix, one matrix model in such a way that this matrix model reproduces the known disk amplitude of DSSIK in the large L limit, where L is identified as the dimension of the Hilbert space of n Majorana fermions, dimension of the Hilbert space of SIK model, 2 to the n over 2. And by matching the measure, mu of theta, and disk genus 0 eigenvalue density of this Hermitian matrix model, we can fix the form of the potential like this, given by some series in infinite series of Chebyshev polynomial with some Q-dependent coefficient. And so this matrix model is called ETH matrix model. The ETH stands for eigenvalue thermalization hypothesis. So what we did is basically replaced the original SYK Hamiltonian by a random matrix. But of course, the SYK Hamiltonian is not a random matrix. It's a system of fermions with random coupling. But this replacement can be justified by appealing to the eigenvalue thermalization hypothesis, which basically says that some universal feature of the Hamiltonian, some random Hamiltonian system, such as the eigenvalue statistics, eigenvalue correlation, can be captured by some random matrix. So that's basically eigenvalue thermalization hypothesis tells us. So this is why this model is called ETH matrix model. Okay. So we just switch gears to consider the matrix model, which is was constructed by matching the SSIK at the genus 0. So we are interested in some large L expansion of some correlator in this matrix model. More specifically, we consider the connected correlator of the partition function, trace e to the minus beta h, but h now becomes a random matrix with some specific potential, which I showed you in the previous slide. And it turns out this correlator has a nice large L expansion with using some basic building blocks. The one ingredient is called trumpet, which is given by this form, where I is just a modified Bessel function, I Bessel function. This is called trumpet. Another important ingredient building block is the so-called discrete volume of the moduli space of Riemann surfaces, okay, which depends on the n length and some n integers. Then we sum over all small b. If you're familiar with JT gravity story of Sachin Stanford, this is looks almost similar to the JT gravity amplitude. So in that case, we have also a trumpet and the volume for the moduli space. But in the case of JT, this small b is a continuous variable, and we have to integrate over 0 to infinity. But in the case of this ETH matrix model, this integral is replaced by the sum, discrete sum. And so this volume can be computed by the method machinery of topological recursion, and I have computed for first few terms. So this volume, and okay. So let's consider the double scaling limit of the ETH matrix model. So by construction, if we focus on the low energy side of the edge of this ETH matrix model, this reproduces the matrix model of Sachin Stanford. And indeed, we can check that the measure factor goes to sinh of square root e, which is known density of states of the short-term theory. So this is just a check at the genus 0, but we can go to the higher genus check, by taking the discrete volume of this ETH matrix model, I can show that this, in this double scaling limit, this discrete volume goes to the Wavy-Peterson volume, which appears in the JT gravity amplitude. So the lower edge corresponds to the ADS version of the JT gravity, as expected. So natural question is, what happens if you take the limit around the upper edge or the high energy side? Of course, I have already told you the answer. It corresponds to the Sitter version of the JT. But to discuss this problem, I have to stress that lower edge and upper edge are not quite equivalent. At the level of the eigenvalue distribution, they look almost identical. So because the matrix model potential is an even function of the matrix, so if you change the sign of the matrix, it doesn't change the form of the distribution. But we should remember that we are computing the correlator of this partition function. And this quantity, the torus e to the minus beta h, is not invariant under sign change of the matrix. So the insertion of this operator into this matrix model breaks the symmetry of h goes to minus h, so they become distinct. So as I said before already, so double scaling limit, if you take the double scaling limit around the upper edge, we get the Sitter version of the JT gravity, which has been studied already by Maracena, Triachi-Yang, and Kotola-Jensen. But if you look at this quantity more carefully, if you change the sign of beta and h simultaneously, this becomes invariant. So in some sense, the Sitter JT, or the scaling limit around the upper edge, is basically given by the analytic continuation of the ADS version of the JT gravity by sending beta to minus beta. But it turns out this analytic continuation is quite subtle. So we have to be very careful to define this analytic continuation. And the subtlety comes from the fact that if you look at the spectrum, E of theta as a function of theta, the angular variable, it looks like this. And this spectrum serves as a potential for the variable theta. And the theta equals 0 corresponds to the minimum, and it corresponds to the ADS version of the JT gravity. But if you focus on the upper edge corresponding to the theta equal to pi, you can clearly see that this is maximum, and this mode is tachyonic, becomes tachyonic. So you have to be careful how to define this integral over the variable theta. So if you naively expand around the theta equal to pi or the upper edge, we get a wrong sign Gaussian integral because it's tachyonic. So to make this integral convergent, we have to rotate the integration contour to the imaginary direction. And it turns out this integration deformation or rotation of the integration contour precisely reproduces the prescription proposed by Kotola-Jensen for the Sitter JT gravity. Their prescription basically says that we have to put factor of I to the genus counting parameter. So basically, the genus counting parameter for the sitter case becomes a pure imaginary I times some real number. And it turns out this I in the genus counting parameter comes from this subtle change of integration contour. Okay. So we can also argue that semi-classical bulk picture of this JT, of the sitter JT gravity. So we can argue at the level of classical solution that the bulk metric corresponding to the upper edge is given by the minus of the metric of Euclidean edges. So in other words, the bulk metric for the upper edge is a minus signature, has a minus signature, which is denoted by minus ADS2. And because of the very strange feature of two-dimensional metric, it turns out this minus of the metric of ADS2 has a positive curvature, so it can be interpreted as a sitter space. So that's why the upper edge corresponds to sitter. Okay. And using this kind of technology, we can compute, in principle, we can compute various quantities of interest in cosmology, like Hartree-Hawking wave function of the sitter space. And Hartree-Hawking wave function is given by the expectation value of the trace of e to minus ILH. So beta, if you take the beta to be pure imaginary, this corresponds to Hartree-Hawking wave function. And L specify the size of the symptotic feature of the sitter space. And we can check that the matrix model result reproduces the result of Malazan-Arturi H. Yang. Okay. Maybe my talk was a little bit too fast, but this is the last slide of my talk. So this is basically the summary of my talk. So the Sashien-Stanford matrix model can be embedded into a finite size matrix model called ETH matrix model. And if you take a double scaling limit around the lower edge, we recover the Sashien-Stanford result. But if we focus on the upper edge, you get the sitter version of JT gravity. So as a future direction, it's very interesting to include the matter operator into this story. So as discussed by these authors, if you include a matter operator, this matrix model becomes a two-matrix model. One matrix for the Hamiltonian and other matrix for the matter operator. So it would be very interesting to compute the cosmological correlator of the matter operator in the sitter JT background using this matrix model technology by taking a double scaling limit around this upper edge. So I'll stop here. Thank you.
So you said like if you double scale at the lower edge, you get the usual JT matrix model, and then you get the Weil-Peterson volume, and then the trumpet for the JT matrix model.
Right.
And what happens if you do the double scale limit in the upper edge? You get the same Weil-Peterson volume, or?
Yeah, same one. Yeah, same Weil-Peterson volume.
Exactly the same.
Exactly the same. Yeah.
And then trumpet is different, I guess.
Trumpet becomes different. Yes, trumpet has, yeah, trumpet carries some factor of I.
Mm-hmm. Okay, thank you.
One problem that was pointed out by Kotler and Jensen, if you make the string coupling imaginary, then the non-perturbative effects become order 1. They become very large. Do you understand, because you come from finite n, how we should think about the non-perturbative completion of this model?
So before taking a double scaling limit, everything is becomes finite, because you can go to the finite n. I don't clearly understand how non-perturbative effects in the Dosita case arises in this whole picture of this. I don't know the answer.
Is it fair to say that you would say that DS2 alone is not consistent, but at a non-perturbative level you have to have both DS2 and ADS2 coexistent?
Yeah, that might be the case. Yeah, but I'm not sure.
Okay, thanks.
Thank you. Very naive question. So when you presented the chord problem, then its solution is given by the finite n Gaussian integral, yes?
Chord problem?
Yes, the number of chords with a given number of intersections. This is the coefficient in one of the in the 1 over n expansion of the partition of the free energy of the Gaussian model.
Not really. It depends on we have a very general definition. We comes with a weight of q. It depends on the parameter q.
1 over n or 1 over n squared, this q parameter.
Q parameter is given by the e to the p square over n.
Well, maybe we can discuss.
Okay.
After the
What is the matrix model description of two-coupled SYK models?
Two-coupled SYK. You can consider the double trace correlator like this. So, and set the random coupling equal for both systems. Then we consider the double trace correlator like this.
But so the interaction between the two models were the common.
So you take so you set both the random coupling same on both two systems, then they start to couple each other. But if you completely set the random coupling completely different, this is just decoupled, factorized.
Set up.
So the next speaker will be Carlos Bercini, and he'll talk about Q functions in n equals 4.
Yes, so thanks all for, just set the timer. Okay, so thanks for the invitation to speak here. Thanks for the organizer for this amazing conference so far. Hope that we also have a great last day. And what I want to talk about today is mainly in this last paper that we did with Till, Andrea, David, and Paul, who like a subset is still around today. And what I want to talk about today is basically like the grand motivation, something that people throughout this conference said, is that we want to use the integrability framework to compute 2- and 3-point functions. And in n equals 4 Superring Mills, in planar n equals 4, these formalisms exist. They go by the name of the quantum spectral curve that you can use to compute 2 points, and the hexagons that you can use to compute 3 points. But also emphasize many times, these 2 formalisms are not in equal footing. Like you can compute the spectrum at some arbitrary value of the coupling, but you cannot compute the 3-point functions in the same way. So one alternative that you can approach is try to make the hexagon more friendly to the quantum spectral curve, try to rewrite it in terms of Q functions. That is one direction that was explained by Benjamin and Alessandro in the previous days of the conference. And another direction that I'll explain today is somehow older. It goes by this name of separation of variables, which can be very technical. But for all the purpose of these talks, the separation of variables will be a machine that eats Q functions and will spit out a number, either 2-point functions or 3-point functions. So in a very pragmatic way, the workflow that I have in mind is something like this. So you know the first step, you know that in conformal field theory, such as n equals 4, 2-point functions of different operators are 0. So this formalism of separation of variables, if it gets 2-point functions, is better if these 2-point functions are different. If it gets 2 Q functions, it spits out 0 if these 2 Q functions are different, and it spits out a number if these 2 Q functions are the same, or if they are associated to the same state. This number, what is the relation of this number with the 2-point functions is something that you have to work out. So the second step is finding this proportionality constants that tells you how this inner product relates to the actual 2-point functions of the theory. And the third step is try to make this inner product a little bit of shell so you can compute 3-point functions. And apart from some semi-classical limits and stuff like that, I will not comment basically. This map, this like 3 steps, have only been worked out in some sectors of n equals 4 Superring Mills at 3 level and recently at 1 loop. What I want to present today is not, of course, this full story, but is this last small development that we have, which is to understand this very first step, this orthogonality of Q functions, not at 3 level and at 1 loop, but actually at many orders in perturbation theory up to wrapping corrections. So in other words, I want to define some separation of variables framework that will give orthogonality of Q functions at all orders in perturbation theory up to wrapping corrections in the SL2 sector of n equals 4 Superring Mills. Let me just remind, the SL2 sector is like these very simple operators. And we are focused on these guys because before wrapping, they are not sensitive to the full 256 Q functions of the theory, but rather they are described by a single Q function or a single set of asymptotic beta roots, which are these Q functions in the QSC language, this Q12/12. And by SOV, what I mean is that we're going to find some simple universal measures that when you sandwich these Q functions with this measure, you get this prototype of a 2-point function. Like if you want like a 2-point function up to normalization, which is this orthogonality. So in order to start, I'll just develop some bases that I need, like some basics works for this SOV framework. I'm going to present our main proposal and also the properties of this proposal. Some are good and some are bad. This is by no means a finished story. So this will be the most complicated, no. This will be the most boring part, which is I just have to define what is the Q functions that I'm talking about and what are the solutions, like what the equations that they are the solutions of. So the Q functions will look like this, like very simple objects. The first part should be somehow familiar. This is the polynomial part of the Q function, which tells you, or these Vn's are the beta roots. So it just tells you that at leading order, and this F is addressing. So at leading order, perturbation theory starts as the number 1, and the Q functions are the normal polynomials that describe most conventional spin chains that you all know better than me. So, and at the beyond leading order perturbation theory, n equals 4 is no longer a spin chain, and these polynomial Q functions will get corrections. And these corrections come in this dressing via the addition of many non-polynomial corrections. So what is this dressing? This dressing can be written like this. The overall shape, it doesn't matter. For all intents and purposes, you can just expand it very easily in perturbation theory. So when you expand in perturbation theory, you see these non-polynomial corrections will be mediated by polygammas that come accompany some conserved charges of the operators. Just to show definitions, so like this is the Zhukovsky variables, like I don't need to define it, but you can see that these charges are very simple objects.
Sorry, so
yes?
So in your notation, is this literally the Q function of the quantum spectral?
It's literally Q1, Q1, Q. The only thing that there is this alpha. I will comment, give me 30 seconds. So this Q1, for example, is the energy up to some factor. And I think like the best way to see it is the Konishi that, I don't know, everybody loves. So this is like the Q function for the Konishi. You can see if you set G to 0 is a polynomial, and then at orders in perturbation theory, you acquire these polygammas that will introduce poles. This is perturbation theory. You're never going to see cuts. So this is the only thing that you'll see, some poles in the complex plane. And these poles are mediated by the polygammas, but also by this alpha, which at the moment, the alpha is something that is a bit mysterious that I haven't explained. This alpha is what we call a dressing constant. And this dressing constant should be 1. So if this dressing constant is 1, this is exactly the Q1, Q1, Q that appears in the quantum spectral curve. If the dressing constant is 0, this is a last, let's say, usual object of the quantum spectral curve, but equally can be easily obtained in mathematical. Just compute this one, polygammas go to 0. So it's a very simple object. It's not natural, but it's a very simple object. And these two particular values of alpha will be important for us. So this alpha is something that we put up posterior, like we'll put in right now, but it's going to be important later. So forget a little bit about like specific values of alpha. So just think of this Q function here. And this Q function satisfies some Baxter equation, which is given here. And it has a shift in the plus direction, a shift in the minus, and then a transfer matrix. And starting from now, I'll do an example, which is twist 2 operators. So twist 2 operators at 2 loops, these are the operators that appear here. So this B plus and B minus are just this, and the transfer matrix is this. You don't need to retain anything of this slide, other than that starting from now and until I say we stop, we're going to talk about twist 2 operators at 2 loops. Okay? And why do I don't talk about the 3 loops and higher? It's because then wrapping corrections start. So everything that I'll say is just wrong if we just keep going in perturbation theory. So if you don't care about wrapping, this is the most orders that you can expand. Okay? And what we want to do now that we survive through definitions is that we want to use these Q functions, and we want to try to set up this orthogonality. And the way that we do it is very well, like it's based on exactly the same idea of Fedor, Kolya, and Andrea, which is just rewrite 0 in a very intelligent way. So why this is 0? You can see this Baxter operators acts on this Q function, and that by definition is 0. This Baxter operator acts on this Q function, that's by definition is 0. So this integral is nothing more than 0 minus 0 is equal to 0. But let's start just to write, let's just write everything that is inside here explicitly. So you have some Baxter, like this Baxter operator, as I said, there is a shift in the plus direction, a shift in the minus, and a transfer matrix. And the same thing will happen here. And now I'll just write everything. This is the only computation I'll do and I'll show. So let me just give you some more details, because if I don't give details of it, there is nothing else I can give details, basically. So this last line is the transfer matrix, and it's the most simplest part we can look. So I'll just write this last line explicitly. It's given by this. Again, you don't have to look at all these things. The only thing you have to look is colors. Orange denote things that depend on the state that you care. These i's appear in the transfer matrix and are the integrals of motion. So each state has their own integrals of motions. So this guy that has spin S has one integral of motion. This guy has another integral of motion. And all this blue part that looks complicated, it doesn't matter, because it's state independent, it's universal. So if I take the first line from the second, everything that is blue drops out. And you start to recognize something that looks like the goal that you want to have, some separation of variables type of integral. You have this difference of integrals of motion, and then some integral, very simple integral of the Q functions. Okay? And this is the notation I use. So every time you see a bracket, just take the thing that is inside the bracket and integrate against mu. So this is what this notation means. Okay? And you can then do the same thing with the shifts. So for example, the shifts at one loop are given by this. You just see there are blue terms that they immediately drop out, and then there are orange terms that depends on the state, and then you get something like this that depends on the difference of these charges, and then there is this Q functions that now appears with some shifts. Okay? You don't have to like, this is just a sketch of everything that I want, that I think, like I hope at least, that I was able to convince that if you do this thing carefully, you start with this guy that is just 0 minus 0 equals 0, you get this sort of equation like this. So what is this sort of equation? So this guy is the difference of transfer matrix, and it's very simple. Then you get some correction at one loop that depends on this charge, another correction at two loops that depends on this charge, and the things that appear inside here are not only the Q functions, but this new object we identify, which we call lower length Baxter operators. So they are the normal Baxter operator, but they do not have the transfer matrix. They're just the shifts. And this just appears, for example, in the previous slide. You can see here there is the shift in the plus direction with x to the 1. So this is just this sort of operators. So this is the equation that we have. And the only thing that we need to do this equation, sorry, I forgot to say something. OK, it doesn't matter. So the only thing that we have to do, this equation, when we write this equation, perhaps I will forget, and then I forgot that I'll say it now. I think it will also make it clear. When you take this line from this line, you have to do a shift. You have to send u to u plus I, right? Otherwise, these lines are not equal. So if you send u to u plus I, this argument becomes this argument becomes this, minus becomes plus, and minus becomes plus. So that's how from this line, from this minus this, you can get this guy. But when you do this shift of counters, the price that you pay is that you pick some residues. And this is the residues that appear here. So this equation is true, provided that you pick residues when you shift the counter. Okay, so this is just a small, caveat that you have to worry, but I always forget because this is the most important part now, is that when you shift these counters and you get residues, the thing that you want to do is to send the residues to 0. And why? This is the main idea, and also it's very based on the things that Kolya, Fedor, and Andrea did. We have this equation that in principle is kind of true for everything because we started from a trivial equation. And now we are imposing some extra condition, is that the residues that appear when we are shifting the counters must be 0. So let me just remind you, for example, at the leading order, so at 3 level, the measure that produces these residues is very special. It's not any measure. It's this 1 over cost squared, which is a measure that is well known and very even old in this language of the separation of variables. But if the residues are 0, let's suppose we are working at 3 level, we just have this equation. The difference of integrals of motion times some integrals of q's is equal to 0. Now you look at this equation and you think, how this equation can be true? If the two q functions are different, the difference of integrals of motion is never 0, because each q function has their own integral of motion. So this delta is 0 for different states is never 0. So the only way that this equation is 0 is if the two q functions are the same. Is the only way that this equation is 0 is if this integral for distinct q functions is 0. So this is precisely what is written here. For this very special measure, and it's unique, this integral of this q function with 1 over cos squared, another q function, will be orthogonal. So this is what is orthogonality at leading order. So this is the prototype of 2-point functions. That you want a 2-point function, you want it to be 0 when the states are different, and you want to be a number when the states are the same. And this is an old story, and it happens at leading order. But what I want to point out is that we can just keep going with the same logic at one loop, for example. So at one loop, suppose that instead of having just like one measure that is 0, have 0 residues, suppose that you have 2 measures with 0 residues. Then one thing that you can do is that you can assemble this very simple matrix equation. This is just like, there will be this equation is equal to 0, this equation is equal to 0. But now you can just run the same argument again. This vector of integrals of motion is never 0, because it's only 0 if the states are the same. If the states are distinct, this vector is never 0, so the only way that you get an equation like this is if the determinant of this matrix is 0. So this could be your candidate of a one-loop orthogonality for the q functions. And you can keep going. For example, at 2 loops, you're just going to get something like this. So you have 3 equations, because you have 3 variables. So you need 3 equations, you need 3 measures, and you can run the same argument. The matrix times this vector of integrals of motion is 0. So if the states are distinct, the vector of integrals of motion is never 0. So the only way that this equation holds is that the determinant of this matrix vanishes. So this is a candidate for a 2-loop orthogonality. So this is how you would do it in principle, order by order in perturbation theory. So how do you do it in practice? Because the only thing that now that you have to find, the only thing that you have to do is finding these measures that they somehow are very special. There are many ways that you can do it, and the way that I do it is very reminiscent of this work that we had done before with Pedro Vieira and Alexandre, which is this. We will make an ansatz for these measures. And I don't have time to motivate these ansatz. The only thing you need to know is that the ansatz is finite. So every order in perturbation theory, we have a finite number of these A's, which are just numbers in principle. Okay? So now, how do we proceed? What is the goal? So we have these matrices that in principle should have 0 determinant. We have the measures that in principle I just made an ansatz for it. So now I just start computing determinants. So I compute the determinant between the spin 2 and spin 4, and I demanded that is 0. I compute the determinant between spin 2 and spin 20, demand it's 0. And this starts me giving equations. And these equations start fixing these coefficients here. And at some point, I have infinitely many states. So at some point, all these coefficients are fixed. And now you have something. You have a measure that is completely fixed. And this is your proposal. So this is your SOV proposal. Either it works or it doesn't work. And how do you know if it works or it doesn't work? You just keep testing another state. So you just test, like, after you fixed all the coefficients, now you test spin 20. Now it either is 0 or is not 0. It's 0. Now you test 22. Either is 0 or not 0. And this is what I call proof by exhaustion. Because you just do it until you're exhausted, and then you just convince yourself. Because that's the only way. And that's what we did. Like after, not even me and my computer could handle it anymore. Like after spin 30, we just realized that everything was fixed and it was keeping giving 0. So either, okay, and this is the result. So the result is this, and this lets me just remind you, this is for twist 2 operators. So you see, the measures are not crazy things, are just very simple numbers that comes together with this tangents. And the matrices are just these matrices. So this matrix, 2, 0, what this notation means is the matrix for twist 2 operators enlarged 0 times. So this should be the usual matrix that, I don't know, people that do SOV should be familiar. And then you see this matrix 2, 1 is the matrix of twist 2 enlarged 1 time by this Baxter, lower length Baxter operator of B1. And this is the matrix 2, 2 that is enlarged 2 times.
So is the statement that all of them work?
No, exactly. So the statement is the following. The statement is, if you take the determinant of this guy, it's going to be 0 plus g squared. You take the determinant of this guy, it's going to be 0 plus 0 g squared, something g to the 4. You take the determinant of this guy, it's going to be 0 plus 0 g squared, 0 g to the 4, then something at g to the 6. The one thing that I want to point out is that it comes out of the computation. Here's where the alpha appears again. So it comes out of the computation. Since we are doing everything numerically, and also, okay, we are, we are free to do anything we want. Like since I was doing all this guesswork, just making ansatz and stuff like that, we can put these alphas there. So you can put these dressings. And then this is also another thing that our computer can fix when you start to demanding that these determinants are 0. And the outcome is that the matrix we find, they are non-democratic. So for example, the first guy, the first state, for some reason, appears with alpha equals 0. And the second guy, for some reason, appears with alpha equals 1. That's just a fact. We don't know how to explain. It's just a solution. It's just not democratic. So the first guy appears as the polynomial part of the Q function, and the second guy appears as the full Q1212. Let me just give you an example. So for example, someone approaches you in the street and say, I want to compute twist 2 states with spin 2 and spin 4. And then you say, okay, what's the first state? Spin 2. You put it non-democratically, so it's just the polynomial part of the Q function. Then there is the spin 4. Spin 4 is the second state. So now it should be the full Q1212 that has polygammas and so on. And now you have to compute the matrix elements. So let me just show you like this matrix element, for example. So this matrix element is here. What is this? This is the integral between minus infinity and infinity of this guy, which is B1. So it's just some very simple shifts. The measure mu2, which is here. And then this Q4. You put this, / n integrate, and then you get this. And this is, okay, I have 0 intuition, it's just a number. But the claim is a number that starts as g to the 0, g squared, and g to the 4. You take these numbers, you do this for all the matrix elements. You put these numbers here. You take the determinant, and this matrix will be orthogonal, it will be 0 plus 0g squared plus 0 2 to the 4, and then it will be something at g to the 6. Yeah, it's 2, yeah, exactly, 2, 4, 2, 4, sorry. Before I had done 4, 6, but I don't know, the numbers were ugly. That's why, I don't know, okay, it doesn't matter. So if you find this beautiful as well, like you have a problem as well, but okay. I think I dive too deep into these things. I'm still recovering. So this is, as I said, so this is twist 2. So twist 2, this is the best we could do. We had 3 matrices that were increasing. And they were increasing 3 times because after some time we have wrapping and then we don't know what to do. Now I want to present what happens, which is our main result, for twist L operators. So in order to talk about twist L operators, I should give you 2 things. First, matrices, and second, measures. Okay? So here's the matrix. Do not be scared. It has a blue part. So okay, notation, MLK. So this will be the matrix that is associated to twist L operators, enlarged k times. If you are familiar with the SOV, this blue part is exactly the leading order separation of variables for twist L operators. So this is a L-1 matrix. So before this talk, if you just delete everything that is orange, look at that matrix will give you leading order orthogonality of twist L operators. But now what I'm saying is that if you want to enlarge it, just add these lower length Baxter operators. So if you want to enlarge it 1 time, add the lower length Baxter operator, so it's twist L, so the first guy you add is L-1. If you want to enlarge it 2 times, add L-2. If you want to enlarge it K times, L-K. And each one of these lines, you have the subscript, 1, 2, 3, 4, What are these? These are the measures that you have to integrate against. And the measures that you have to integrate against, the mu1, mu2, mu3, are there. So these are the measures. They have some 3-level part, and then they have this part here, which just is this. It's a closed formula. Like there is no free parameters anymore. Either this is correct or is wrong. There is no other way. And here, there is this infinite. This infinite is how many loops you want to compute. So if you want to compute 10 loops, just put the number 10. If you want to compute 20 loops, put the number 20. And if you want to compute some sort of finite coupling, I have some sort of, I can resum all of this, and it's in the end. This is in the bonus slide. I won't show. I don't want to scare anyone more than this already is. So this is it. And the claim is very simple. You take 2 states of twist L. Now, you can create these matrices. So the matrix of L enlarged 0 times, the matrix of L enlarged 1 time, 2 times, and so on, until the last matrix enlarged L times. And the claim is that the determinants of these matrices will give you 3-level orthogonality, 1 loop orthogonality, 2 loops orthogonality, 3 loops orthogonality, until you have L loops orthogonality. And then you cannot go any longer because you have wrapping. And again, I don't know what you do when you have wrapping. In other words, you can just write it in this very simple way. The determinant of this matrices is going to be sometimes some 0 plus something that starts at the next leading order. Except, okay, this is the big elephant in the room. I'll tell you a little bit more in the end. Except when the states have the same twist and the same spin. Okay, so just leave it here. I'll not forget. But it's something that is the worst part of our formalism and the worst part of our expressions. I will show you this. Okay, for sure there'll be questions, but I will just leave it here, and then we can talk it just a little bit in the end. So let me just, before I talk about this, I just wanted to give you an example so it becomes a little bit clear. What do I have in mind? So suppose, okay, you're walking downtown London, and then someone will say, look, I want to compute twist 4 operators. One has spin 4 and the other has spin 6 at 3 loops. So what do? You have this matrix that, you have twist 4, so you know that a 3-level is given by this matrix, 4, 0, which is a L-1, L-1 matrix. So it's a 3 by 3 matrix. And you say, oh, I want to compute it at 3 loops, so I must enlarge it 3 times. So now it becomes a 6 by 6 matrix. You take the measures, you compute the Q functions at 3 loops, you compute the measures at 3 loops, you put it in Mathematica, you do n integrate, and then you get a matrix like this, for example. So this is the first column of the 6 by 6 column. There is this other column, then this goes until, I don't know, a couple meters. And then so it's a 6 by 6, and you can see like all the entries are ugly. Like there is no entry that is particularly nice. All of them have a term at g to the 0, a term at g to the square, a term at g to the 4. There is no reason unless for this matrix to have this behavior. But indeed, if you take the determinant of this matrix, you get the number 0, then the number 0, then the number 0, until you reach g to the 8. So that's how you operate with these guys. And there are three properties that I want to talk about in this last 5 minutes, or okay, 4. Which is, there are good properties that are unexpected. There is this bad property that I have to address. And there is a strange property that I don't know. Depend on who you ask. And the collaboration is split, if this is bad or good. So the good property, and it's also good because I want to talk about now, which is offers a little bit of a physical intuition behind this expression that it looks ugly, which is the following. Suppose you have a twist L operator and a twist L minus 1 operator. Okay? So operators of different length. And now you just have this blue part, which is a result. It's like a matrix. You take the Q functions of this twist L and twist L minus 1 and just plug into this matrix. You just want to see what is it. Is it 0? Is it non-zero? What is it? And you can just compute, and it's non-zero. And there was no reason to be 0. It's like orthogonality between states of different length. However, if you use these enlarged matrices, so suppose you add the operator of twist L minus 1 on this line, this Baxter operator, when he acts on the operator of twist L minus 1, gives 0. So you have an entire line that is made of zeros. So these enlargings, they are making some sort of trivial this orthogonality of twist L operators with twist L minus 1 operators. And that's how you should view these enlargings. So every time you enlarge it, you make the guy that you want to make, these twist L operators, orthogonal to operators of smaller and smaller and smaller sizes, until you reach the size 0, basically. So that's how you should see these enlargements. And okay. And then the bad property. So the bad property, let me just explain it just like give you an example and why I haven't talked about it before. When you do twist 2 operators, for each spin, there is a single operator. So it's something that I could not tell you before because it doesn't happen for twist 2. It's something that we start observing on twist 3 and higher. And what is it? If you take twist 3 operators, you start numbering your states, and then you see, for example, at spin 6, there are 3 states of twist 3 that have spin 6. These 3 states are orthogonal to all the other states of twist 3, all the infinite number of them, but for some reason, they are not orthogonal amongst themselves. And this is just like, it was just because when we were doing this, when we were trying to find these expressions, we never tested for this by miraculous coincidence. And then it's something that we tried in the end, and it doesn't work. And it doesn't work, and I cannot tell you why it doesn't work. I could say, like, I have no idea is a bit harsh. We have, like, epsilon idea of why it should be. There is, like, a small section in the end of our paper that, like, is an attempt of explaining how this could be resolved. I cannot explain, but I'll be happy to talk to anyone after this talk and try to address this problem. But I think it all boils down that our approach, since I come from the bootstrap community, my approach is very unanalytical, I would say. I was just guessing and having some feeling and trying to find these expressions. And in the end, we end up with this thing that I do not have, although I can offer you some interpretation of these enlargements and so on, and some motivation where they come from, I cannot give you like an honest and nice analytical derivation of everything that I did. And I think this is deeply related to the fact that I cannot give you an explanation why these operators of different spin are not being orthogonal. And I think just like this is also one of the big motivations that I want to present it here, because there are many people here that understand more than I do about these things. And I believe that if we have this analytical understanding of not only this derivation of this result, but also how to make all the states orthogonal in this way, we can not only compute orthogonality, but then focus on the actual thing that matters, is that when things are not 0, when you have the norm of the states. Because then we can actually compute 2-point functions with this formalism, and perhaps in the future compute 3-point functions as well. So that's what I want to say. Thank you very much.
Questions?
Yes.
Fedor.
Anticipated.
Okay. I just wanted to ask, like, did you explain what was that strange property?
Ah, yes. No, the strange property. Sorry. Yes. Yes. So the strange property is the following, is that, okay, thanks. I had 19 seconds, I should have done it. Okay, but the strange property is the following. If you have some sort of SLV formalism, the thing I would expect is that every time you enlarge it, you change your definition with the Godin norm, but in a perturbative way. So if I do things at 3 level, I enlarge it one time, you should only change the normalization with the Godin normal, with the 2-point function, at 1 loop. And then if I enlarge it 2 times, it should change it at 2 loops. This is not what we observe. So every time you enlarge it, you not only change the perturbative definition, but also the overall 3-level prefactor. So that's, I don't know, that's a fact of life, and I don't know how to, yeah. So perhaps let's call strange/bad then. I think that's, I'm in the 25% of the collaboration that believed was good, but okay. But I can give you more details why I think. Let me just point out, like in this last section of the paper where we attempt to do more analytical results, we end up with a different formulation. The price that you pay is that it only works for twist 2 operators. We don't know how to generalize. And in that case, indeed, it happens what I said. At 3 level is the same, and then it only changes at 1 loop. So, okay. Sorry.
One fast question. Do you incorporate the dressing phase in some way?
Yeah, like for example, at the beyond 2, like twist 2, like it doesn't happen, right? But for all these other guys, when you are solving the beta equations and so on, the dressing phase is there. Yes.
And one deeper question. Do you have any maybe speculations about the representation theory or any algebraic interpretation of your result in some more invariant terms?
This equation reflects on me and goes to Paul. Like it's the.
I understand you may not have.
Yeah, no, I don't have it.
Or anything.
I don't have even the speculations, but if there is a person in our collaboration that can speculate on that, it's Paul. I simply cannot.
I mean, in this SL2 setup, not really. So we did similar things in SU2, which are not in the paper, but nevertheless we did them. But we tried to look for like an underlying spin chain interpretation coming from everything, and more or less we just reproduced theta morphism. But yeah, that's all I can say about that.
Charlotte?
Just the obvious naive question. Is there any hope that it can be used for computation of 1-point functions? And
oh yeah, no, that's it's one of the future directions, something that really want to do it. Yes, yes. Yeah, okay. To get the actual number is always complicated because of this normalization, but it's something that is on our radar, yes.
Okay, previously people for twist 2 states, they studied the generalization of these Q functions for the continuous spin S.
Yes.
So is there any hope that you can extend your orthogonality formalism to this continuous S case?
Yeah, no, that's a dream. Actually, like next week I'll be in Brazil, and that's exactly what I want to do with Pedro there. So, so yes, it's exactly what I want to do, and it's yeah, it's the hope. And also, let me point out that I think like this is the way to also explore other limits, such as large spin in this formalism. That is something that is also not well understood yet, as far as I know. Like yes. Okay.
Thank you.
I don't see any other questions. Let's thank Carlos for a very nice talk. And, very convenient, 25 minutes past 11.
Can you hear me? Because I got here.
Can you put it, yeah, like a little bit more to the center? Not a big deal, but just in case you turn your head.
Which side?
Just like right below your.
Oh, it's now it's on. Thank you. So again, I would like to thank the organizers for inviting me, and this has been a wonderful conference. It's my first time at IGST, and I've had a lot of fun. So I'll be telling you mostly about some work in preparation with my collaborators, Prokopi, Volodya, and Harish. But I'll also say that there's been some earlier work that has addressed some of these things. In particular, last year, there was this paper of Kazakov, Harish, and Pedro. You might have heard about it last year in IGST. So there's some updates to this, and you might not be aware, but I also worked on this before. So what am I going to tell you about? So before I tell you about anything, usually when people talk about ADS-CFT, they like to say that there's a natural hierarchy for operators. So for n equals to 4, at least in the half VPS sector where I know what I'm talking about, people will say that, well, depending on how the dimension of the operator scales, you get different things in the bulk. So if delta is of order 1, you should expect that it's some kind of graviton or some KK mode. Usually people say operators with dimension of order n are giant gravitons, and operators with dimension of order n squared are dual to geometries. Great. But if you work on this seriously, you realize that there's always a lot of caveats to these statements. So for example, for the single trace, there's mixing between single traces, so the KK modes are really dual to some kind of complicated combination of single trace operators, and well, actually multi-trace operators. The giant gravitons, really, the classical solutions in the bulk are dual to superpositions of these operators, not to particular operators. And really, my point is, more importantly, that for the geometries, not every operator with dimension of order n squared is dual to a geometry. It really has to be generic enough. Okay, so what do these things mean? So some questions you might have when you're working on this is, well, what kind of operators can I even play with this game? So could I take something like trace c to the k to the n squared, or trace c to the n squared, or combinations of these things? And if I do this and I somehow manage to compute correlation functions, how do I see the shape of the geometry that's dual to this operator? And I think what's really the hardest question is, how do you do the opposite? If there's a geometry that I want to prepare, how do I prepare the state in the CFT? And really, it would be nice to be able to do this efficiently. If you're more ambitious, you might want to do this in less supersymmetric setups, but okay. And basically today I'll try to answer this four points and give you some hints about this last one. Okay, so why is large n hard? Well, here we usually talk about when people say n equals to 4, they drop the planar n equals to 4. So even in the free limit, n equals to 4 Young-Mills is not really a free theory. For example, you can look at this correlation function and you find that there's mixing between different multi-trace structures. So it's really a free theory with constraints. So you should think of it as some kind of topological theory of interacting strings. Of course, in a planar limit, this is not an issue. But as soon as delta gets really large, these effects can't be neglected. And eventually, they actually overpower everything. So how do you solve this problem? Well, the honest approach is to diagonalize two-point functions, find operators that have properly orthogonal, do it in the free theory, and then if you want, you can do perturbation theory. So for half VPS operators, this was beautifully done by this paper by Corley, Jabik, and Rangulam. There's a basis of orthogonal operators for UN. So it's a beautiful solution. But already, if you add one more matrix and you start to ask generic enough questions, these techniques get really, really intractable. So if you want to see what these things look like, there's a recent review by Demilokov and collaborators. So I'm not going to be honest. Instead, so the reason this problem is hard is because you're asking for exact orthogonality at every n, and that's very hard to do. So instead, I'm going to ask for something that's closer to approximate orthogonality. So I want states that don't have sort of delta function. Well, yeah, so the two-point function of two operators is approximately a delta, and then there's a kind of exponential tail to when it's not. Yeah, I think that's the typo. And some of my collaborators, and for instance, Bernstein we have been trying to develop tools to address these problems in BPS sectors, in particular half BPS, core BPS, etc. Yep. So what are some kind of operators that you should keep in mind that I'll be talking about? Well, you could, for instance, try to come up with these combinations, something like this. Like you could try putting a potential for C. So this is what we call exponential operators. Now, I'm not the first to think about these things. At least in this context, the first time this appeared was in a paper of Sam Vasquez in 20 years ago. There's, of course, the orthogonal basis. And the thing that I'm more excited about are these coherent states. Okay. So none of these, except for the characters, none of these have definite dimensions. But I hope that you appreciate that this is not really a bug. This is something that I want. Okay. So half VPS operators. So, well, in general, half VPS operators, when people talk about them, are just spanned by multi-traces of a single complex matrix. So essentially, this was known for a long time. This means that the Hilbert space of half VPS operators is isomorphic to n-free fermions. And it turns out that it's n-free fermions in a harmonic oscillator. So you can think of a wave function of one of these free fermions as being some kind of distribution in the large N limit. And this is where a lot of people got a lot of mileage here. They used this implicit duality to these free fermions, and then they would compute. But actually, it's not very easy to reduce honest correlation functions to the free fermion description. But this description is quite nice because it's quite explicitly matching the dual supergravity solutions. So clearly, if you give me an operator that's excited enough, it will lead to a density of eigenvalues, and that gives me a geometry. But how to do the opposite is a bit more tricky. And the simplest things that you can think about are 3-point functions of these half VPS operators. And just by symmetry, so these are not, in general, primary. They're going to be sums of structure constants with some kinematic functions. For now, I will set this essentially to 1. And it's known that these structure constants are independent of the coupling. So sometimes when I talk to people, then they go, well, this is not really interesting. There's no coupling dependence, so they're trivial. But there's really 2 parameters. There's n, and that's a different kind of coupling. Okay. So a lot has been done before. I'm not the first one to look at this. So for example, for structure constants of 3 light operators, essentially, I would say about everything is known in the large N limit. For correlation functions of giant gravitons and light operators, I would say we know most things. Other things you could repeat are more complicated. And really, we know very few things about heavy light, especially on the gravity side. So today I'm going to tell you about these heavy light operators, more importantly, these heavy giant correlation functions, and maybe some things about heavy. Okay. So what's the trick? The problem with this kinds of calculations is that if you're doing things honestly, you're doing a lot of weak contractions of free fields. And operators are normal ordered, so you either have to be very smart at combinatorics or you have to do things by hand, and it's very tedious. So it's always useful to try to come up with a different perspective of a combinatorial problem that might help you solve it. So here the trick is, well, we want to map this to some kind of matrix model because we know that at least the spectrum is related to free fermions, so there should be some matrix model description. So first, I'm going to write down the most naive thing that I could write down. So I'm going to replace all the scalar fields by matrices, drop all the space-time dependence, but keep the R symmetry dependence. And then you can ask, well, what's this integral? What's the value of this correlation function in this Gaussian ensemble? And at first, this was a complaint that I had about this. This couldn't possibly give you the right answer because these are not operators. They're not normal ordered. But actually, because of this, these polarizations are null, you can easily see that if you do Wick contractions between this operator, they'll vanish. And similarly for the other two. So the only things that this computes are basically Wick contractions between 01, 02, 01, 03, etc. So this is exactly the same combinatorics that you would get from, say, doing this in free Yang mills. Okay? And then you can use the Birkenfeld symmetry to fix your polarizations to be your favorite. So I can pick the first operator to be made out of C's, second one to be made out of C bars. And for the third one, I'm basically left with this freedom. And then you just integrate all the things you don't want. And very clearly, this is going to give me a matrix model for C and C bar. But OK, we still have to work because these things don't commute. So you can't reduce it to eigenvalues. But OK, you go and do a lot of work. You go open some books about complex matrix models. And you see that the right thing to do was this short decomposition, and that you should integrate over these upper triangular parts of the matrix. And luckily, for all the things that we care about, these things are Gaussian. So we can actually just do the integrals. And we get something like this. So now this is a purely eigenvalue expression of some different function, which we call the Q transform of the operator. So it's given by this integral, which you really should think of as some kind of normal ordering. So if f was some kind of trace of x to the k, this would be some matrix analog of a Hermite polynomial. Okay. And the point is, we can do this by hand. We can actually compute these things explicitly. And OK, so the strategy is, at least for heavy, heavy, light, heavy, heavy, giant, you determine the distribution of C's from the integral, and then you evaluate this last operator in that distribution. Okay. So first, I have to tell you how to get that distribution. This is a well-known problem. Usually, these things are referred to as Ginevri ensembles. So here I'm going to be formal, and I'm just going to say that the potential is the log of the operator, but this doesn't change the argument. So the saddle point equations for this come from an effective action and the large n limit. And the only important thing is that this V and this V bar are holomorphic and anti-holomorphic. Because then the saddle point equations will tell me that this rho is constant. So it's going to be constant in some domain, possibly disconnected. And so the problem is, how do you reconstruct this domain? So this is a well-known problem. This is Laplacian growth. And it turns out that you only need holomorphic data to reconstruct. So for example, you look at a character. This is what the matrix model would look like. The saddle point equations have this solution, and you find that the distribution is some kind of concentric ring distribution. So this was well known. If you take something like a cubic potential, you can play around with the parameters, and you can make all kinds of shapes. Again, this is well studied in matrix models, so I'm not going to dwell on this. But the ones that I do think I need to dwell a little bit on are these coherent states. Because, well, in general, if you look at this expression, it's some messy determinant. So you would really think that you would have a very hard time finding the saddle point solutions to this. But it turns out that these things are, they're coherent states, and I keep calling them coherent states. So because they satisfy this coherent state condition, if I apply the C-bar operator on the state created by a coherent state, it just returns the same function with a scalar. Okay. So if I assume that the saddle point condition still applies, and then I use the coherent state condition, so I compute the expectation value, some holomorphic quantity. A large n, I expect that to be an integral over the density. But I know that because it's a coherent state, it's actually given by a sum of these coherent state parameters. So what you do is, well, you push this integral to the boundary, and what you find is that, okay, there's poles. There's poles at the positions lambda I, and essentially, I mean, the math words are that the Schwartz map of this domain has some poles and some analytic part, and yeah, so the point is you can actually reconstruct this shape. So for example, take the simplest distribution of these lambdas that you could think of. Say I put n over 2 of them at some point alpha, n over 2 of them at some point minus alpha. So the moments are always going to be given by this. And in that case, so you plug this into this formalism that I was talking about, and you find that the shape of this algebraic curve of the boundary of the droplet is given by this. And so in math, this is called the Neumann oval. But in physics, this geometry was actually already considered by in a paper of Skaders and Taylor. They call these Riplon geometries. So this is the case for k equals to 2 of this Riplon geometry. So what does this thing look like? If you take alpha to be close to the origin, it looks essentially, this is not quite a disk, it's a little bit shifted. And then you keep messing with it until they kiss, they disconnect. So essentially, I can make any kind of disconnected domain with these coherent states. And of course, I mean, I can put different numbers of eigenvalues at the nodes. It doesn't change anything. And in fact, I can put any kind of distribution. As long as I know the analytic structure of the distribution, I'm able to find a conformal map to whatever the shape is. So for example, this distribution is a semicircle for the lambda eigenvalues. And it turns out that the shape of this domain is an ellipse. So for this distribution, it actually just reproduces the quadratic potential. If you take a uniform, sort of like a line of charge, you get some kind of oval shape. I don't think it has a name. Okay. So basically, in general, if I superimpose these coherent states and I take the Larsen limit, I'm able to get more and more of these nodes. So I get more general quadrature rules. And then depending how I play with these things, I can get higher order calls and so on. So if you look at some theorems about these quadrature domains, you find that these things are dense. So actually, I can, in principle, reconstruct any shape with these coherent states. So that solves the problem that I was telling you about. But okay, in practice, you might find multiple domains with the same moments. So you have to pick the one with maximal action. We haven't encountered one of these examples yet, though. But they do exist. Okay. So let's do all the heavy light operators now. So I know how to get any kind of density now. Now I just need to find what the right things to put in the matrix model are. So you look at these kinds of expressions, and you open the book by Ekhammar and Bressan on background field methods, and they tell you all these formulas on how to compute these kinds of things. So, okay, here I give you the first 5. In the Larsen limit, okay, the first one is given by trace x. X is QC plus QC bar. So it's a Hermite polynomial. The second one is a Hermite polynomial. Third one is a Hermite polynomial. Fourth one is not a Hermite polynomial, but it's a sum of Hermite polynomials. But okay, everything is a sum of Hermite polynomials. But these coefficients, I mean, if you look closely, these are basically binomial coefficients. They're just entries in Pascal's triangle. So I think there's a lot of structure here that is not really obvious. Okay, so you go and you expand in this parameter Q to extract the different charge sectors. You go and work out the normalizations, and you get these kinds of expressions. And then you open Skaders and Taylors, and you find that this is exactly what they find. Up to some normalization. So to me, this seems to say that there's a lot of hidden structure in these correlators. Somehow, maybe there's a This suggests there might be a simple way of doing this calculation, Skanders and Taylor, but I'm not sure. Okay, so now let's replace a trace by a determinant. Again, you just basically plug this into the formalism, you crank the thing, and you get some expression in terms of eigenvalues. Okay, and then you integrate, you get at the end, say, a structure constant of some representation R and some subdeterminant of rank delta. You get this kind of integral. Here H is related to the Young diagram. So this matrix is not very clear what this is until you work out a couple of examples. So if you have a Young diagram like this with 3 blocks, it turns out that this matrix will have 3 blocks. The size of the blocks are related to so these heights, and these L's are essentially the distance to these corners. So because it's block diagonal, it just reduces to each of these blocks. So it factorizes. And for each block, you get some tridiagonal matrix, so the determinant satisfies the recursion relation. And if you work with matrix models a lot, you recognize that these are orthogonal polynomials. So in this case, these are associated Hermite. Okay, so again, you open the textbook and you compute. So that's the value of the structure constant, and this is exact. Okay, but I said I wouldn't do combinatorics. So how do I get this a different way? And the point is that the expectation value of this determinant in the C ensemble is related to the exponential of the resolvent, the integral of the resolvent of the density. And I call it P because you should really think of it as a momentum. And this expression is just the WKB approximation of the orthogonal polynomials I was talking about before. Okay. So you can plot these things. They don't look, so this gray line is the exact integrand for some parameters. You plug in the asymptotics, they don't look too good. But of course, it's because you're only looking at the asymptotics. You're not looking at the fine grained details. Okay. So as we heard yesterday, usually when you get oscillatory integrals, you have to deform your contour and go through a complex saddle point. So that's what happens here. You deform your contour, you find a saddle point for this integral, and it's given by this in the end, where this B and this A are the radii of the ring distribution that's created by the big operators. Okay. And this you can rewrite like this, but okay. And this is actually exactly the asymptotics of the previous expression. Okay. So unlike single trace operators, these things grow exponentially. So I expect that if we were to compute this in gravity, the only thing that you would get to leading order is the asymptotics. And because it grows as e to the n, it looks like a D3 brane, but it can't be a full D3 brane, so it has to be some kind of instanton. Okay, I'm not going to bother too much with this interpretation, but the point is that essentially there's 2 contributions to this OPE. One of them comes from an integral over the density, which I call the sort of a bulk part. And then there's an integral that only depends on the data of the dimension of the operator that you're measuring. So this is some kind of boundary condition, some kind of boundary term. And there's always this common alpha squared plus epsilon over 2. You can always check that this is inside the distribution. So this to me says that there's some kind of hole in the distribution. Okay. So now I'm just going to, actually I went too fast, but I'm going to flash some other things that we can do. So I think last year, Harish gave this really nice talk, short talk, where he was working on the numerics for heavy correlators. And I think last year he showed you a plot where he had these dots making this shape. Now we actually have the analytic solution. We have the solid line, and that's the actual eigenvalue distribution for this potential, at least when you take the operators to be determinant C to the n. Okay. We can also do this with cubic potentials. So Prokopy very heroically worked this out. So this is the density. And well, here you have two parameters, so you can play around and you can tune the thing to a critical point. So you find that at least this correlation function seems to have critical behavior that's similar to the three-state plots model in Integrability. Okay. And now, okay, the thing I would really like, I hope there was a lattice person here, but I don't think there's any lattice people. So now, Corey BPS operators. It turns out that there's a natural generalization to these coherent states that I was talking about to the Corey BPS case. Now, in general, I don't know of any construction of Corey BPS operators in n equals 4. As far as I know, this is a very hard combinatorial problem. So this, in some sense, is a generating function, but we don't know what it generates. So if you take this coherent state and you set these coherent state parameters to commute, you can show that this is annihilated by the dilatation operator up to 2 loops. We can't check 3 loops because we don't have the non-planar dilatation operator at 3 loops, essentially. And in general, these things will lead to unsolvable matrix models. I tried very hard. Me and my collaborator tried, and we couldn't make a dent. But there's still coherent states, so they still satisfy this nice condition where as long as you take expectation values of holomorphic observables, they're only replaced by by proper scalars and not operators. So I somehow expect that these things are related to, at least approximately in the large limit, they should be related to commuting matrix models, but I don't know how to make this precise. But if you could do this, and I think in principle you could ask this question of how can you reconstruct the dual geometry to one of these operators? And it would be very similar to what the half EPS case, how the half EPS case worked. I don't know how to do this, and actually the duals for these operators are very complicated. And another comment is that these kinds of integrals seem to be related to what you would do if you did a quenched Eguchi-Kawai reduction, the principal Carroll model. Unfortunately, the quenched Eguchi-Kawai reduction doesn't seem to work even for gauge theories. I think it's the people that seriously work on this, I think they don't believe that this, well, never mind that, but they say it doesn't work. But there's a working model of this Eguchi-Kawai reduction, which is a twisted Eguchi-Kawai reduction. And there might be some relation between that and the beta to 4 n equals to 4, but we don't know. Okay, so conclusion, BPS coherent states are very nice. They allow you to control essentially the whole parameter space of the Hilbert space very explicitly. There should be a similar story for Corey BPS operators, but I don't know how to, essentially, I don't know how to deal with these matrix models. I showed you some examples of the things that I could do. So these are, I cherry-picked one correlator that I could show you explicitly, but in practice, you could do whatever. Like, for example, if you pick some potential, you should expect that the recipe tells you that the expectation value of a determinant is going to be related to the orthogonal polynomials of that potential. So we can compute these things. I think at least in the Salpon approximation, I think now I understand that we can really do this explicitly. But we don't really have a very concrete gravitational interpretation for these things. And I think it would be very nice to work this out. You should also take this as evidence that large n superYang-Mills makes sense, not only in the planar limit, and it might have a controllable semi-classical expansion. Okay, I talked a lot about free fields, but I could have just replaced free field with chiral algebra and everything works. So I think This is not special to these half BPS operators. This is something different. Okay, so thank you.
Are there any questions?
So just a bit technical question. So you showed that like a normal ordered version of the trace of some power, like a trace of some like a field to some power,
Yes.
is some linear combination of Hermite polynomial. I thought like it's more related to Chebyshev, but maybe we are talking about something different.
That's what happens. I'm not. So to be completely honest with my Mathematica skills, I was only able to get to 6, and there's this pattern. Harish claims he can get up to very high numbers, but we haven't checked. But for sure, so the Hermite polynomials come from this normal ordering.
Mm-hmm.
So that one definition of the Hermite polynomial is you take the moment of x plus iy to the k. It's that kind of thing.
I see. So you don't see any relation with the Chebyshev?
Not here, but I know that, I mean, when we were computing these other things, we got all kinds of Jacobi polynomials. So I right now I don't see the relation, but maybe.
Well, if there are no more questions, let's thank Adolfo again.
I will have some events